So one of the things that we do in data mining models is every time we are running a model, we have to understand and assess what the performance of that model is with reference to some sort of standard, some reference point we should have. And this is something which is very important as a preliminary step when we are getting into data mining, because since today, if you are comfortable with programming, there are so many different libraries. You could easily start running different libraries. It ends up creating several solutions for businesses that are not really consistent with what the objectives were. In fact, some of these have resulted in losses for companies also. In fact, one of the examples that I mentioned, or one of the slides that I had shown in my first lecture, was indicating that there were several failure stories of data mining. And the reason is we are not necessarily looking at data mining models with respect to how it's performing vis-a-vis its objectives. All right. So that's something which I wanted to bring upfront rather than doing it in the end, so that you know that whenever we are pursuing data mining models, we first of all understand the objectives, we understand what kind of data it is, pre-process it properly, ensure that we have transformed the variables if needed. And then we also ensure that we're evaluating the performance as and when we run the model. So this particular topic is going to be relevant as an important topic throughout all the different modeling techniques that we will learn. For every modeling technique, we can evaluate performance. And there is an error metric that we want to minimize. And we want to know what those error metrics are, how we calculate them, how do we reduce them. So that's the agenda. And then we will get into the first machine learning model, which relies on multiple linear regression. So the question obviously is, why do we have to evaluate a data mining model? The reasoning here is that there are so many different methods available. You have multiple linear regression that we're going to cover today, then k-means clustering, there is neural networks. So there are several different techniques, and there are different techniques that you can use for classification, classifying customers of different types, or classifying employees of different types in companies, for example. Or you could use these methods for prediction, which customers to target, for example, so that you increase your revenue. So there are different methods. And for each method on top of it, we have multiple choices that we have. Right? So it's not just that we use k-means clustering, and then within that itself, we have several options that we could use. So this increases the possibilities of using a machine learning model or data mining model. So therefore, it's important that whatever model we are choosing in the end, we have ensured that it is performing the best among all the possibilities that we have for this. So this is where we'll get into some understanding of how do we evaluate both predictive performance and classification performance, because we will have some tools that we will cover over the course of several weeks, which talk about predictive modeling, data mining models that help in prediction. And then there are certain tools that help, there are data mining tools that help with classification. These are important business problems that we always encounter. So we will see both kinds of models. So when we are evaluating performance, the outcome that we are looking at is either a numerical value. We are predicting something, let's say what the sales are expected to be if we were to choose this customer, right? So that's an example of a numerical value that we are predicting. It could be membership in a class, which is classification problem that I just mentioned, that segmenting customers, for example, high-paying customer versus low-paying customer. That could be an example here. Or the third one could be an outcome, which is the propensity, which is how much is the probability of something belonging to some class, whether a customer belonging to some class, employee belonging to some class, a product belonging to some class. So these are the three typical types of outcomes that we will encounter in data mining models. So if we were to start with the numerical value, which is what we do in prediction, we would like to see what is the error in that numerical value that we predicted using data mining, and then try to minimize it. Now, it's many of you are familiar with linear regression, right? I mean, can you show a show of hand how many of you are familiar with multiple linear regression? Good. Two. I see some few of you have experienced multiple linear regression. Now, multiple linear regression, the way you may have learned in statistics classes, is where we are explaining something, right? We are using regression model, we get coefficients, and then we are explaining what are the variables that could impact our y variable, how the association between all the x's with the y variable is. So, for example, the price of a product, how it's the weight of the product, energy efficiency of the product, etc., could impact the price. So that's one kind of modeling. This is what we typically learn in statistics. But in data mining, we are using multiple linear regression for a very different objective. We are not trying to explain the data. We are trying to predict a future, a data which does not exist in the current data set, so that we can see whether whatever we have created as a model, does it provide a good assessment of any new values that we have to predict. So therefore, this predictive error is not like the goodness of fit that we see in our multiple linear regression models, because we are interested in predicting new data, not how well our model fits the current data, which is what we do in statistics. And the way we normally measure error is the actual y versus the predicted y. So if we have to predict something in the future for certain y, and the actual y is later on observed, we take the difference between the two, and that would be the error that we have, right? So normally when we look at the error measure EI, this is E subscript I, that's the error measure. We always are looking at the actual, which is y, minus y hat. So whenever we have to show predicted values, we always put a hat on top of it. So in this case, these are some of the measures of error that we typically would use in machine learning models, in different data mining models. One is the mean absolute error. Basically, take the error, which is the difference between the two, take absolute value of it, which means that all the negatives also become positive, add them, and then take the average, right? So add all of them and divide by n. N is the total number of observations. So that's, again, mean absolute deviation, or these kinds of errors also you may have experienced in some other contexts. But we use similar error measures also in data mining. The mean absolute deviation or mean absolute error is one, where we take the absolute value. We can just take the average error, where we are not taking the absolute value. So we let the pluses and minuses remain the way they are, and then we take the average. And then mean absolute percentage error is when we take the error, which is the difference between actual minus predicted, but every error is then divided by the actual. So you can see EI divided by YI, which is every error that we have for the predicted value, we divide that by the actual value, so that we know what is the actual percentage error. When we multiply it with 100, we are trying to determine what is the percentage error that we have in our model. Or root mean squared error, which again, we're looking at square of the errors first, adding them together, and then taking an average square root of that, right? So that's something which can be used. And total sum of squared errors. So there are several techniques that can be used. I'm just trying to highlight some of these here. The actual expressions or the mathematical expressions is not important, but it's important to realize that we could be using these kinds of metrics. Now, sometimes what happens is our data is not normally distributed. We always assume that our data is normally distributed, but oftentimes there is high level of skewness. It's a shifted data, long tail data, and all that. So in that case, when we have outliers, when we have several values that are very high or very low compared to what the regular other values are, sometimes we'll have to use median-based measures. So instead of mean absolute error or mean absolute deviation, we would use median absolute error or median absolute deviation. So the only difference is that we are not taking the averages, rather we are looking at the median values of the error. right? So that's a better metric, especially when you have outliers, when you have data which is not normally distributed. The other thing which is very important when you are analyzing data and evaluating performance is you always try to plot histogram or box plot. So for this, I have a code which is also provided to you in the reading. So every data set that you are trying to analyze before you start running the models, you also want to ensure that you understand what that data looks like. And then the error that you are getting because of what you predicted versus actual, how that is distributed in the histogram. So this is a histogram, and this is a box plot. So this is the training data, and this is validation data. In data mining, we will soon see that we always try to split our total sample into two parts. We have a training sample, and then we have a validation set. This is training set and validation set. So it's always more important that our error in the validation set is low. Right? Training set, because we are training our model on a given data, it is going to be low. That's expected. So it's not necessarily going to be beneficial for a company. What is more important is, can we bring down the error in the validation set, which was not used for training the model? And that's something which, for example, here we can see, we look at the error pattern for validation set. We look at the error pattern for the training set. If they look relatively close enough, that's sort of a signal that our model is not that bad. I mean, it's predicting both relatively closely. Although in this case, you can see that you have a little bit of distribution, which is different between the two in terms of the spread that you have here. And especially in the box plot, you can see that for validation set, you have certain outliers that are going out here. And for training set also, you have certain outliers here. So this is a way you are trying to compare not among models, but between two different data sets. One is the training set and the other is the validation set for a given data mining model. And that's the comparison that is often very important, because the errors that are based on training set is only telling us how well the model fits the data, which is not useful in data mining and predictive modeling, because that's something which we do in explanatory modeling, in regression used in statistics. Whereas errors based on validation set is what tells us whether the model is able to predict new data, how well its predictive performance is. So that's really more important, and that's something which we try to focus on. We will always expect training errors to be smaller than validation error. That's an expectation because our model was run and trained on a given data set. So it is learning that data very well. So it always tries to minimize the error in that data. But the key is how well it's performing in the validation set. That's something which is important always to keep in mind. Now, if it's a very complex model, when we get into deep learning models, and there are several complex models, you'll see that the model that you're trying to train on a training set, it starts to overfit the data in training set, which is also not good. You'll start seeing that your error metric for training data is almost zero, because the model has completely learned what exactly is there in the training model, because it's a very complex model and you've been able to capture all the patterns that exist in the training model, training data. So that's sometimes what happens, which is an overfitting the training data. And in those cases, you'll start seeing a greater difference in the error within the training set and validation set, which actually is not a good sort of situation to be in, because you may have predicted your training set perfectly, which means you have almost zero error. But then your validation error will be non-zero, and how much it is away from zero is an important criteria that you have to keep in mind. Right. So therefore, it has to be done through comparison of error plots, different metrics on both training and validation sets. So along with those error metrics that we just talked about, there are certain graphs and charts that can be very helpful when we are understanding how well the model is working. And these are what we call cumulative gains and lift charts. This is again a metric, a measure of error that we can capture through this. Now, lift charts basically is a form of a graph that is used when our goal is to search among a set of new records. So we have all these new records. Which records among them, a subset of them, can give us the highest cumulative predicted value. Suppose we have like 100 values in the validation set, 100 different records that we have, and we are now predicting, let's say, the price or the sales that we will do to these 100 customers in the validation set. We are trying to determine a small subset of customers who will probably give us the highest cumulative predicted value, highest, let's say, sales in this case. So that's what the lift chart does. It compares the model's predictive performance to some baseline where there is no predictor. So we are not using any predictor. What happens in that case? Versus if we use predictor of the customer's sort of characteristics, their salaries, their income levels, etc., and their place of residence, whether these kind of variables actually help us lift how many of these customers will provide us the most revenue. This is something which we try to do, and we'll see an example later. So it's for a continuous response like price, revenue. These are continuous variables. We talked about continuous variables, categorical variables in our previous lecture when I was talking about data pre-processing. There are different types of data. So when it's a continuous response, we can use lift chart. And it's relevant when we are searching for a set of records that gives us the highest cumulative predicted value, like I mentioned for the revenue from a customer. And it's not relevant when we are interested in predicting the outcome value for every single new record. We are not interested in that. We're just cumulating it and trying to determine how many of these customers can provide us the most. So every single customer we cannot predict as well with this particular technique. So the way it works is we use the y-axis in which we are putting things like revenue, price, all those things that I just mentioned. It's a continuous variable. For a customer, we are trying to understand how much revenue we can get. For a product, we can determine which one will have higher price customers will pay. So y-axis will have all these numerical target variables, all these kinds of variables. And x-axis will have the number of cases, in other words, number of customers, for example, or number of products in a descending order who are providing us the most returns, most revenue, most price. So we are trying to put them in order in such a way that the first one gives us the most benefit, the second one after that, a little less than that, but more than others that are in the list. So we are trying to put them in a descending order of predicted value. And then we benchmark this, whatever we got from this kind of a graphing of y-axis and x-axis, we benchmark it with an average numerical value where we are not using any predictor. We are just basically randomly determining who will provide how much price, or which product will have what price, or what customer will give what revenue. We are randomly doing it. That's one way to do it. It's called naive approach, right? So that's naive approach, that we are not using any predictor, no data mining model. We are comparing this data mining model against a benchmark, which we call a naive approach. And what the lift curve does is, the farther away it is from this naive diagonal value, the better the model will be, right? This is how it looks like. So if you notice that this is a lift curve or cumulative gains chart, so it's sort of in both terms are used here. So this, again, you have a code for this data set that I have also provided to you. And what you're doing in this case is, it's a car rental company, and they always renew their fleet. So it's a car rental company. They buy new cars, and after several years of using, after a few months of using, sometimes they want to renew their fleet. And whatever these old cars were, they want to sell them off. Right? So now, not all of these old cars they can sell by themselves, because their primary business is rental cars. They are not into used car sales business. So what they do is, a large chunk of these cars that have to be sold, they give it over to a dealer who is selling used cars. But they keep a small proportion of cars that they want to sell themselves, which they think will give very high revenue. Right? So they have several cars that they want to sell. Some of these cars they want to sell themselves through their own channels, but a large chunk of other cars they don't want to sell themselves. They want that to be disposed of to a dealer in volumes, large volumes. So they want to identify which are those cars that they should sell themselves, because that can increase their revenue, right? Which is basically which one will fetch them highest cumulative price. So that's what this particular model is, where on the y-axis, it's a cumulative price that you can expect for a car. And x-axis, you have the number of records, how many cars you're going to sell, which will give you whatever returns it is. This diagonal, the dotted line, is your naive approach when you're not using any model and you're just naive. You're modeling it, just assuming that it's randomly. You can choose any car. So if you notice at 57, so on the number of records, sales of 57 random cars, if this point is about 57, sale of 57 random cars will result in about $613,292 for the company. So this point, the blue point here, is about $613,292. But if they were to use the data mining model that is there, it lifts up this curve such that it can fetch them those 57 properly selected cars, not randomly selected, but the ones which are selected through data mining model, can fetch them $1,089,905. So what that tells us is, if we take the ratio of these two, 1,089,905 divided by 613,292, the lift that we are getting by using a data mining model is 1.78. So we can increase our revenue, our price that we are going to earn by 78%, right? So that's what we can identify with the help of the model. So higher this value, better it is, better model it is. And the same information that we can get from cumulative gains chart or lift chart, we can also get from a different chart, which we call a decile chart. So this is an example of a decile chart. Again, a code that provides, which helps in creating this kind of a chart, is also provided to you in the reading. What the decile lift chart does is it basically divides the data into 10% sort of decile, 10 deciles, right? So 10%, 10%, all the way till 100. And what we are trying to do here is we're choosing the top 10% of the car that gives the highest predicted sales. That is coming from the data mining model. So in this case, we can see that top 10% of cars, by using the data mining model, gives us a lift of 1.76. Around 1.76 is where we are here. So that's sort of, it gives you 1.76 times the revenue rather than using 10% of the cars at random. So for this company, it's important to choose the right cars that they want to sell from their own channel. This was predictive performance. As I mentioned earlier, data mining models can be used for prediction. Data mining models can also be used for classification. So what if we have to judge the classifier's performance rather than predictive performance that we just talked about? So here we have not yet looked at the classification models yet. The data mining models we're going to cover as we go further, but I'm just trying to highlight that sometimes we are doing classification using a data mining model, and we want to know how much error exists in the model because of the way we have classified. So we are interested in misclassification error, which is classifying a record as belonging to one class when it actually belongs to another class, right? So we would, if you want to know which customers are high-paying customers, we want to segment our customers properly. We want to segment our suppliers properly, for example. Ideally, what we want is we segment them appropriately. The ones we think are our strategic suppliers, according to the data mining model, also show up as strategic suppliers. And this is when that does not happen, when there are certain suppliers which are not strategic suppliers, they are shown up as strategic suppliers. There's an error here. They're classifying belonging to a strategic class when actually they are not. So that error we want to capture. And the error rate is percentage of these misclassified records out of the total number of records. So total number of suppliers, or total number of customers, how many such instances exist when we misclassified it. Again, benchmark to understand how well we are doing with the data mining model compared to not using it or using something else is the naive rule, which is, in this case, unlike what we just talked about for the prediction, naive rule is, what if we classify all records, which is to be in the future, we have to predict. We assume that all of them belong to the one which is the most prevalent class. So if our customer base is segmented into, let's say, high paying, medium paying, and low paying customers because of their characteristics, right? So some subsidy customers versus otherwise. And let's say the medium paying customers are the largest number compared to the other three categories that we have here. What the naive rule does is, for every new record that it's going to see, it assumes that it belongs to the medium paying customer base. So that's the naive rule. Um, and we are comparing, we want to do better than that. Using a data mining model, we want to make sure that we are able to classify better than that naive rule of just classifying based on which one is the most observed in the existing training data, because it's what the validation set classification that we do matters. It's not the training set classification. So that's ideally what we want to do in most cases, but there is an exception in certain situations, and I'll talk about that later. Sometimes we are interested in identifying high value but rare outcomes. Right? Sometimes we are interested in specific situations which actually gives us very high returns, but they happen very rarely. In those cases, we actually would want to do worse than the naive approach, naive rule that we have here. So we will talk about this later. When does that happen? When would we want to do better? When would we want to do worse than that? For example, tax frauds, things of that kind, which typically happens rarely, but it could be a high value items. And there we would want to do something different in terms of how we compare against the naive rule. So we will take a look at this later. Now, classification essentially is separating records into different classes. Right? So we sometimes will have high separation of records, which means that using our predictive variables, we are able to separate easily and we get low error. And sometimes we would have low separation of records. So in this case, we have less number of data, and we can relatively easily separate owners and non-owners in this data set. So on owners and non-owners using income and lot size of their houses, using these two predictors, we are able to more or less distinguish them. There are few which may not come into the proper. So if I create a line like this, I could be getting most of the owners separated out from non-owners. But in this case, we are using annual income and monthly credit card average spending as two predictive variables to sort of uh, determine whether they're going to accept a sales offer or they would not accept a sales offer. Suppose that's our objective here. We can see that this is a very large data set compared to this one. We have several dots here. And at the lower end, we are pretty clear. It's very easy to separate out the gray ones and dark sort of black or dark gray. There's a difference between the two. On the lower end, relatively easily distinguished. But as we get to the higher values around this point, it starts to become relatively difficult to separate, because there are some of these non-acceptors who have high annual income and have high monthly credit card average spending. And there also are several acceptors in the same set, same place. So there are both kinds of data sets that we can have, low separation and high separation types. Now, when we are going through classification models, we will see that later. We typically would want to see how well we have classified actual class versus our predicted class, right? So we are predicting that uh, this particular case belongs to this class. This customer that we are predicting for will belong to this class in the validation set. So if we take actual class as 0 and 1 and predicted class as 0 and 1, right? So what we can see is that if we predicted 0 when actual was 0, that's great. If we predicted 1 when actual was 1, that's great. Whenever we are predicting 0 when actual was 1, that's an error. predicting 1 when actual was 0, that's an error. So these two are actually our incorrect classifications. 85 ones that are incorrectly classified as 0, and 25 zeros that are incorrectly classified as ones. Right? So this is what we call confusion matrix, classification matrices. Both terms are used. And error rate, if we were to capture that, so 25 plus 85, these are the two errors that we have here, divided by the total set we have is 3000. Total number of values that we have here is 3000. So we have an error of 3.67%. And accuracy is 1 minus error, so which is 96.33%. So in a binary set like this, where we have actual class either 0 or 1 and predicted class either 0 and 1, it's sort of easy. We could easily see the confusion matrix and determine the error rates. Sometimes we will have multiple classes, right? So we could have 0, 1, 2, low, medium, high, for example, and predicted class also 0, 1, 2. And then we will have more number of rows, more number of columns. So in those cases also we can calculate error rate. Just a little bit more calculation here. Sum of all the misclassified records divided by total records. So same idea, but now we have multiple records that we are misclassifying. Now, in classification, when we are doing all this classification and confusion matrix, most of these data mining models, they typically use two-step processes. For each record, first they will determine what is the probability of this new data belonging to a class 1, whichever class we are talking about, a high-paying customer, for example. And then we compare it with some cutoff and classify accordingly. So there is this benchmark, a cutoff value that we are using. So we look at the probability, compare that probability with a certain cutoff value, and then we classify them as 1 or 0. Now, default cutoff value for the probability is 0.5, 50%. So if we are greater than 50%, we classify as 1, less than 50%, we classify greater than or equal to 50%, we classify as 1, less than 50%, we classify as 0. So that's a default cutoff value, but there are different cutoff values that can be used. But most of the time, you would use 0.5 because typically error rate is lowest when you're using a cutoff of 0.5, 50% or more. I'll show you how the error rate increases or decreases as we change the cutoff from 0.5 to something else. So for example, if we are trying to determine from a data set if a person is an owner or a non-owner of a property using different variables that we use for prediction, what we are going to do here is actually whether they are owners or non-owners is this column. And then we put all the predicted probabilities in descending order here. So 0.9959, the first one, we are 99% sure that it's an owner, 98.75%, and so on and so forth. Now, when we use the cutoff of 50%, anything above this value, we are going to consider as owners, especially the ones which are, owners, and we have correctly identified them as owners. It tells us how well we have done. So in this case, 11 records classified as owners among the top values here. So these are the 11 records. So if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So those are the 11 records classified as owner when the cutoff was 0.5. Now, if I look at the predicted value with cutoff of 0.8, now in this case, we will have 7 of them as owners, right? So that's it's changing in terms of the number of owners that we have. So I can take a look at how much will be the accuracy, which we know 1 minus error rate. We just saw it in one of the previous slides. How much is the accuracy we get if we would have chosen the cutoff as 0.5 versus 0.87 or 0.25 or 0.75? So we have a code, and again, I provided that in the reading, that can tell us using different probabilities how much is the accuracy that we're getting. So in this case, as you can see, for 50%, the accuracy is 87.5%. For 0.25, it's 79%. For 0.75, it's 75%. So typically, this is the accuracy, how accuracy goes with probability cutoffs. And we can see that around 0.5, we typically have the highest accuracy. And as we go away from 50%, the accuracy typically goes down, and the error typically goes up. Right? So this is what normally happens when we are doing classification and looking at confusion matrix for different cutoffs. Typically 50% is what we use. Now, I use the word typically, we use 50%, which means that there are certain circumstances when we may not use 0.5, even though we know our error is going to be high. Right? And those are situations when one class is a bit more important to really determine than the other one. So we just saw the confusion matrix with 1 and 0 actual and 1 and 0 predicted, and we identified what the error rate is. Our assumption was that predicting 1 and predicting 0 is equally important. But in some cases, predicting 1 may be actually more important than predicting 0. For example, credit default for a company, they want to know who are the ones who will default, and that one is more important than those who are not going to default. Or company which is sending response to a promotional offer, sales offer, it's more important to know who are the ones who actually will accept that offer than those who don't accept the offer. So sometimes one class is more important. And in such cases, we actually can tolerate a little higher overall error because we choose a cutoff which is not 0.5. And in return, the advantage is that we are able to identify the important class, which requires more attention because it helps us increase our revenue. Here are some accuracy measures that we use. We just talked about confusion matrix a while ago, and we looked at what the accuracy was in that confusion matrix. But there are a few other alternative accuracy measures. Sensitivity is one, which basically is also called recall. What it tells us is if C1 is our important class, like the ones who are going to be responding to a promotional offer, for example. So sensitivity of the model will be percentage of the C1 class, those who belong to that class, that we correctly classify. That would be our sensitivity of the model. So N11 basically means that it is belonging to class 1 and we classified it as class 1. So that's what our prediction was, divided by all those that were part of class 1 and we classified as class 1, those who were part of class 1, but we classified them as class 2. So we are adding the two types of classes that we have, but ones we classified as 2 also are added because that's an error we have here. Right? This one was an error. This is actually correctly done. So we're looking at sensitivity as how many did we correctly classify compared to the total number of classifications, which include the ones correctly done and the ones which were not correctly done. So that's sensitivity. Specificity is percentage of class 2 class correctly classified. So it's basically just the opposite of sensitivity in terms of the second class. So second class N22 means the class 2 actual that we predicted as 2. So that's correctly classified, divided by class 2 that we predicted as 1 plus class 2 that we predicted as 2. So those we classified correctly as class 2 and those we did not classify correctly as class 2. We classified as class 1. So this summation will be all the possibilities that we have for class 2. So that's specificity. Sensitivity and specificity are two important measures that we always see. We will be seeing it many times when we are doing classification types of models. And then we have precision. Precision is percentage of predicted C1s that are actually C1s. So we predicted something as C1s and it actually happens to be C1s. So this is something which is slightly different from sensitivity, right? So sensitivity and precision, it also says C1 is correctly classified, whereas here also we are saying percentage of predicted C1s that are actually C1s. This is a difference, which is the sensitivity, high sensitivity would be, for example, let's say a test identifies most people who actually have a disease, even if it also flags some healthy people as having the disease. So it identifies most of the people who actually have the disease in that model. And some of these healthy people are also flagged as having disease. That's something which will have high sensitivity, which is high false positive rate. right? So if we are looking at a bunch of patients and we want to distinguish between those who have the disease and those who don't have the disease, a model which has high sensitivity would be the one which would basically identify most people to have disease, although it may be flagging some of those healthy patients also to have the disease. But high precision model would be one which will only flag those people that have the disease when they truly have that disease. But by doing so, it might miss some cases of the disease. So there could be some of those who have disease actually are missed out, but it will only flag when they have disease. That'll be an example of high precision, right? So that's low false positive rate. So one is high false positive rate, high sensitivity, whereas high precision is low false positive. So those are the metrics that we use. Sometimes we also use false discovery rate and false omission rate as alternative measures. Percentage of C1 class incorrectly classified and percentage of C2 class incorrectly classified. So incorrectly classified is it was class 2, but class 1, and we have classified as class 2, right? So that's something which is the error that we have here, divided by the total number of class 1. And then this one is percentage of class 2 that was incorrectly classified. So there are all these metrics, we use them in combination because that way we are able to ensure that we, depending on the context, we are choosing the right model. Now, another way in which we capture the error in classification often is what we call the ROC curve. Essentially, ROC stands for Receiver Operating Characteristics. It's a term that was originated in World War II, and it was applied to radars. And the objective was to measure the effectiveness in identifying enemy aircraft using these radars. So distinguishing between signal and noise, right? So that's what the original objective was, but this happens to come handy in the data mining models. Essentially, you see that this ROC curve has the y-axis as true positive rate, which is the sensitivity, which we talked about. The sensitivity is true positive rate, C1 class correctly classified as C1. And false positive is 1 minus specificity, right? So this is specificity was the C2 class that was correctly classified, but we're doing the false positive, 1 minus specificity. But there are certain softwares that also use specificity rather than 1 minus specificity in this ROC curve, and they reverse the scale here. So it'll go from 1 to 0 rather than 0 to 1. Right? So you could be finding some softwares who might use an x-axis which uses specificity and go from 1 to 0. But we are using false positive rate, 1 minus specificity, so it goes from 0 to 1. And true positive rate, which is sensitivity, which goes from 0 to 1. Now, what we are doing here is looking at the area under this ROC curve. So the diagonal is your random classification, just like the naive classification we talked about, randomly assuming that they belong to class 1 or class 0. If you do that, we basically have this diagonal line that basically captures the idea of random classification. But if we are using a data mining model, we are doing better than that. So essentially, what we are doing here is we are looking at how much is the area that is under this ROC curve, that is this orange line. More the area that we can cover. So ideally, if we have this orange line going all the way and basically going like this, that would be the 100% curve area. But in this particular case, it's 93.75. The area is 0.9375. So 93.75% of the space is covered by the ROC curve. So this ROC curve is another way in which we can determine how good the model is, how well the model is performing. And again, I've provided you some codes to calculate and to find this ROC curve for a given data set. So something which another way to do that. We are still using sensitivity. We are still using specificity values here, but we are converting that into a sort of a graph, which helps us capture a little bit better understanding of it. Now, I mentioned some time back that sometimes you have asymmetric costs, which means that for one class, if we misclassify we actually end up having higher costs than the other class. So one class is more important than the other class. That happens oftentimes in certain circumstances. If you look at it in a different way, if we correctly classify a certain class, we actually are able to benefit more than if we classify the other class. Sometimes that happens, like classifying highly paying customers and then targeting them with our sales campaign can give us higher revenue, right? So sometimes it's asymmetric in terms of how we want to approach the two classes. So we will take that example also a little bit and try to understand how performance measures errors can be captured in that case also. So suppose, take the example here, suppose we're sending sales offer to 1,000 people, where on average, we will see 1% of people will respond as one, that they will accept the sales offer. Right? So out of 1,000, 1% are responding as one, which means 10 people will respond as, they would like to access, they would like to get this sales offer. Now, a naive rule, like I mentioned earlier, it'll classify everyone as zero because the error rate is one. So we'll get an error rate of 1%. Everybody is zero. 1% who were going to say one, you're classifying them also as zero in the naive rule. So overall, your error happens to become 1%, right? You sent it to 1,000, but you're assuming everybody is going to be zero. Therefore, you decide not to send or whatever. So in that case, your error will be 1%. Very good error. But if we were to use a data mining model and we know that identifying these ones is more important than zeros, the non-responders are not as important as the responders because these responders are going to give us revenue. And I'm more interested in identifying these responders. If I were to use a good data mining model, suppose, and I can classify 8 of these ones as ones. So this particular cell predicted as one, they were actually as one. So 8 of them were in this class, and we correctly classified them as one. And it comes at a cost of misclassifying 20 zeros as ones. Right? So we also classified 20 of these in the data mining model that we just created. Suppose once you learn the classification model, our data mining model classified 20 of these zeros also as one. So that's an error, right? It's a misclassification. So the total error is how many did we predict one, which actually was zero, 20 of them. How many did we predict zero, which actually were one? There were 2 of them. So these two together will be 22. And 22 out of 1,000 total number of people results in 2.2% error, which is higher than this naive rule of 1%. So this is basically an example that I just showed here is when we are looking at sending sales offer that's to be mailed to a random sample of people. And the offer is going to be accepted by 1% of these households. And we are looking at those who will respond to the offer versus those who don't respond to the offer. Those who will respond to the offer are going to give us some profit, right? So whoever is a one, if we were to correctly classify them and we send that sales offer to them, they give us a profit of $10. But there's a cost of sending these sales offers, mailing them, whatever the cost might be. $1 is a cost. So suppose we use a naive rule and we classified everybody as zero. So we will not send anything because we have classified everybody as zero. We are assuming that nobody's going to take up our sales offer. So we would have no costs, no profits, right? So it's a dead even. But if suppose we go with the data mining prediction and we sent 28 offers based on the model, because if you notice here, there are 28 of them we predicted as going to be one. Out of them, 20 of them were incorrectly classified, but 8 were correctly classified. So we will send it to these 28 people who we classified through data mining model. And we send these sales offers to them. And these 8, which we correctly classified, will respond and accept our sales offer at $10 each. So $80 we get there. 20 will not respond because they were not going to accept it. So we spent $1 each. So we have spent $20 over here. And then 972 of them, we are not sending anything. So this way, our net profit will be $80 here minus $20 that we get here. We spent in sending our mails. So $60 is the net profit that we get in this case. So which is actually better than no cost, no profit situation that we had in the naive rule, even though we ended up having higher error in this case. Right? So that's an example of what happens. So this is the profit matrix for that, $80 profit from this particular cell and minus 20 cost from this cell. So that's something which we are going to think about, with the classification that we have obtained here. You can also look at it from a cost curve. And that is when we capture also the opportunity cost, right? All kinds of costs that we have to incur, including the opportunity cost. The opportunity cost when we are not sending anything. In the case of our naive rule, we are planning to send nothing because we assume everybody is zero. So there we have these 10 ones because there is 1% of the population, 1% of those 1,000 people who are going to accept. Since we did not send to anybody, we missed out on those 10 ones. And those 10 ones could have given us 10 times 10. Everybody gives us a profit of $10, which we would have gotten $100 here. We missed out on that. So that's the opportunity cost if we were to use the naive rule, right? Whereas if we were to use the data mining rule that we just talked about, the cost will be, we did not send anything to these 970. So that's okay. So we will have $20 for each of these people that we sent our mailer, everyone $1 each. There is missed opportunity from these two. Each of them could have given us $10 each. So there's an opportunity cost of 20. And then these 8 also we sent a mailer. So $1 each. At that rate, it's $8. So total $48 is the opportunity cost plus the cost of mailing. So even if you look at it from the profits perspective or cost, including opportunity cost, the data mining model has done better than the naive rule. So this is something which sometimes is beneficial even when we have a higher error rate than the naive rule. So sometimes we do this. Now, when we're trying to improve the actual classification of a model, sometimes we want to incorporate that cost of misclassification as part of the model and optimize our models. So because we just talked about what's the profit that we can earn, profit matrix, what's the cost that we are incurring, the cost matrix. So if we want to improve actual classification, it is also possible to incorporate that cost of misclassification as part of the evaluation of the model performance measure. So we are minimizing basically the cost of misclassifying a class C1 record as belonging to class C2. So Q1 is the cost of misclassifying the class 1 record as belonging to class 2, and Q2 is the cost of misclassifying a class C2 record as belonging to C1. So these are the two costs we are multiplying to the number of cases that we misclassified. So this is something which we can use as part of our model evaluation. It so happens that when we are minimizing this, the thing which matters is basically only this ratio. We want to see what is the ratio. The parameter we want to consider is such that the ratio of misclassifying a class C1 record as belonging to class C2 record in the denominator and misclassifying a class C2 record as belonging to class C1 in the numerator. This ratio is what we want to minimize. So even though this expression is bigger, basically it ends up becoming like this. So that's how you can improve the actual classification by incorporating some of these optimization within the model. We have yet to get into these models, but I'm just highlighting this, that there's a possibility of doing this. Now, if suppose sometimes we have a sample that is over sampled in one class. Like for example, we are looking at a set of customers, and large majority of them belong to a certain class compared to the other ones. There are very few who are high-paying customers. Majority of them are basically looking at a low-cost offering from the company. So if one class is oversampled in the sample, now we would like to correct the average misclassification measures because this is a distorted sample proportions. And we look at it in terms of the probability of the proportion, the true proportion of C1 and true proportion of C2. Basically, the same model that you have here, but now we are multiplying this with the proportions also. So this is something which I think is helping in optimizing the quantity by looking at the ratios, not only the cost, but also the probability of misclassification. Right? So this is something which we will talk about later in oversampling. Um, but the goal of ranking performance basically is to detect among a set of new records the ones which most likely belong to a class of interest. For example, tax cheats and debt defaulters, etc. Or in our case, the example that we just looked at, responding to a mail which ends up in a sales offer. And we need to describe lift charts, lift curves for a binary outcome that we just saw, which helps us select a relatively small number of records. And then those small number of records can lift our profitability beyond the naive approach of randomly deciding who it is. We saw that example. So that was used for predictive performance. Same idea applies for ranking performance also when we are ranking our customers. Now, if a particular class is relatively rare and of much more interest than the other classes, then we need to sift through the records and sort them according to which ones will be most likely representative of a particular class. So we are trying to describe the case in which our goal is to obtain a rank ordering. So this ranking performance is we are trying to rank our predicted values in the validation set in terms of most likely, less likely in terms of getting an offer, sales offer, and things like that. So that's classification versus predictive performance versus ranking performance. So it's the same idea, except that we are using lift chart in this case for ranking our predicted values belonging to a certain class. So the way it works is, suppose we have the propensity of one, which is the probability of something being one, class one, and the actual class happens to be this value in this column. Some of them are one and some of them are zero. Notice that for the first 7 of them, the actual class is 1, and we have very high probability of them being of the same class, right? So that's, if you cumulate that 1 to 7, but this particular one, the one which is observation number 8, we had a 76% probability that it's class 1, but actually it is class 0. So the actual class, it remains at 7 only because we were incorrect in this particular one. So we basically are looking at the cumulative actual class by looking at how many, based on this probability, were actual class ones that we correctly understood as class 1. And using that, we can create this cumulative gains chart. So you see that the diagonal is the same naive rule where we are randomly considering each record to be of a certain class, whereas the data mining model looks at each class and then predicts based on the probability. So first 7 of them, it keeps on increasing here. So as you can see, the cumulative value keeps on increasing until 7, and then it remains at 7 because we had incorrectly predicted for one of them. And then once again, it goes up. So what we are seeing is there's a difference between the diagonal line and this cumulative gains curve. Right? So similar to what we just talked about earlier when we were looking at the predictive performance. And that also can be examined with this decile lift chart, where we divide this data into 10% deciles. So there are 10 deciles of each. And what we see is that the top 10% gives us a lift of 2 times, right? So if we were to correctly predict, rank order them, we get benefit of twice than if we were to use a naive approach. So this is another way we can determine whether we are working with the right data mining model or not. Is the model working well for us? Now, all these examples that we just talked about were for binary 0, 1, two classes, but we could sometimes have multiple classes, let's say M classes, which means that the confusion matrix will have M rows and M columns. I talked about this earlier. There doesn't have to be just 0 and 1. You could have low, medium, high. So in that case, you'll have multiple rows and multiple columns, but it creates complexity in the model, right? So there will be theoretically M times M minus 1 misclassification costs. And any class can be misclassified in M minus 1 ways. So instead of 0 being class 1 being classified as class 2, that's only one possibility here. If we had 3, class 1 could be classified as class 2 or class 3. So there is M minus 1 ways. So 3 minus 1, 2 ways misclassify, which results in too many different misclassification scenarios to work with and increases the complexity. Interestingly, in most of the decision-making contexts, such complexities don't arise. And even if it arises, we try to bring it down to one class that is what we are trying to predict. And then rest of them we consider as sort of class 2. We combine all of them, rest of them as class 2. So we try to convert them into a two-class kind of a problem to make it easier to understand. But doing a multi-class scenario can still be possible and can be done. Right. So the gains and lift chart that we just saw for two examples, we could incorporate the costs and benefits in these. We looked at the examples with respect to how much the lift was as compared to the diagonal line. And now what we can also do is we can incorporate the costs. So when the benefits and costs of any correct classification is known, we need to know what exactly the advantage of correct classification is. Like we saw the example of that sales offer. When we correctly classify, we get $10 profit. When we send these sales offers as a mailer, we spend $1. So there's a cost, there's a profit, there's a benefit and cost here. So if that is known, we could use the gains and lift chart by incorporating those costs and benefits. So we could take into account those aspects also. So we have a step-by-step process here. We sort the records in descending order of predictive probability, which is what we do in any case. We just saw the example of lift chart where the probabilities were in a descending order. Then for each record, we will record the cost or benefit associated with the actual outcome. So $10 profit, for example, or $1 cost of sending the mail. Then for the highest propensity, which is the very first record, which has the highest probability, its X value will be 1 because the first record, and the Y value will be its cost or benefit. So it's not the count. So we saw this example where the Y was cumulative gains in terms of the number of the counts in terms of how many we correctly classified. But here, what we're saying is the Y-axis will now change to the cost or benefit. So we could do that. So then we do the same thing for the next record, calculate the cost benefit associated with the actual outcome, add this to the cost. So we're keeping on capturing the cumulative profits or cumulative loss. We keep doing this step 4 until all the data sets, all the points have been covered. And then that would be our cumulative gains curve incorporating costs and benefits. Again, the reference line will be the diagonal line. And we want to see how much additional profits we can earn by doing so. Now, sometimes the lift curves can also go negative, right? So if total net benefits from all cases is negative, your reference line will have negative slope. Suppose even if I were to send to every single one all the sales offers, and I realize that the total benefit is actually a negative value, what will happen is we will end up having a reference line which is a negative slope line, and we are comparing it. So this is an example where if I were to consider the diagonal, instead of diagonal being like this, it's a negative sloped line where we are spending more as we send the mailers. Right? Let's say the cost of mailing to a person is 65 cents, value of a responder is $25, and we have a response rate of 2%. Now, suppose we send 10,000 mailers, then because the 2% people are responding, we get $25 from them, and that would be 2% of 10,000 multiplied by $25. That's the revenue we're getting. Minus the cost of sending to 10,000 is 65 cents multiplied by 10,000. So total cost that we incurred here is minus 1,500. So expected net value of mailing to a list of 10,000 people is minus 1,500. So that's the straight line going from 0 to minus 1,500. So that's this reference point, right? This line. And using a data mining model, if we can create a lift curve and determine at what number of mailers we actually end up getting the most profit. So in this case, if we do the lift curve, once we are able to go through these models, we could look at what number of cases, once we send them, we actually earn the most profit. So mailing to about 3,000 people in this case ends up being optimal. So that's something which we could do as part of analysis of lift curves and understanding of the models itself. So this is another thing which we will be observing as we get to these different models. Now, oversampling and asymmetric costs, I talked about this earlier, that sometimes you have asymmetric cost because you have certain cases that are rare, but they are important. These classes are more important, even though they are rare. For example, those who respond to mailing, those who commit fraud, those who are debt defaulters. A bank would want to make sure that they capture the debt defaulters because that would hurt their disbursements. So what we do in those cases is, and these are not very large number of people, right? Most of the people don't default, but the small set is a very important set. So we have to oversample these rare cases to give more information for the model to work with. Because if they are very less, and we are running a model with that less number of sort of cases that are debt defaulters, etc., then the model will not be able to capture the essence, the key patterns. So we want to oversample these rare cases. Because if we do simple random sampling, we will end up having very few of these rare cases. We would use a different type of sampling, which we call stratified sampling, which means that we first of all create two stratas, one who are these kinds of classes that are more important, debt defaulters, etc., and the other ones are the ones which are less important. And then for each of these stratas, we sample records and then use 50% ones and 50% zeros for training. So we try to use equal number of this important class and the other class when we are training the data. So this is something which we do, and that's something which we will see in three scenarios as we see later in the next few slides. The optimal classification when we assume equal costs of misclassification. If we misclassify and zeros, we give them higher cost, because that class is more important. So if we misclassify the debt defaulter, we want to give 5 times the cost of misclassifying those who don't default. That's another way to do it. And the third one is oversampling. Like we ensure that we oversample these debt defaulters or those who will respond to our mailer so that the data mining model can incorporate this asymmetric cost. So if we were to assume equal cost of misclassification between these two symbols of classes, right? So if O's and X's. So we will classify this as O and this as X. So what we see is that there's an error of one O being classified as an X. But what if the O's were more important? They're very less in number, but they're more important to classify correctly. So what we can do is we classify in such a way that O will be given 5 times the cost if we misclassify it as compared to misclassifying X. So when that happens, our model will predict it'll create classification something like this. It'll classify the two O's correctly as O's, but in doing so, it also classifies these two X's as O's, which is incorrect. And it classifies these X's as X. So this would be a situation where we ensure that the important class is correctly classified, even though we have classified these X's also as O, which is an error here. But that's something which is, depending on the context, important. And this is oversampling scheme where, because these O's are important, but they are rare, we oversample these O's to appropriately weight misclassification costs. So we have more of them, and then we classify O's and X's. So that way we again are classifying it like this. So these are the ways by which we could be working on classification and ensuring that we make sure that we are sampling it correctly and ensuring the costs are correctly done. Now, oversampling, when we do this, they have to adjust for it because clearly the real data does not have as many rare cases. But when we did the training, we oversampled it because we wanted the training model to learn more about these rare cases. So what we will do is we have to then adjust for the oversampling, which is by scoring the model to a validation set where we don't do any oversampling. So we do the oversampling in the training set, but don't do the oversampling in the validation set. In the validation set, we want to use the same sort of the way it is randomly there. And then score the model to an oversampled validation set and reweight the results to remove the effects of oversampling. So this is another way of doing it, that you oversample validation set as well, just like training set, but then the reweighting is done to remove the effects of oversampling. So that's another approach that can be used. So normally the process is when you have very low response rates, typically the practitioners will train models with 50 responders and 50 non-responders, the two classes, and then validate the model with an unweighted sample for the original data. So simple random. So in the validation model, typically you don't oversample. So this is a normal process that practitioners use when they have cases, situations where some of these classes are rare. So how do you oversample the training set? The rare cases responders, let's say, and the normal highly available class is non-responders. You'll randomly assign half the responders to the training sample. So the way you will create the training set is you will try to separate these rare classes with the non-rare classes. First, you randomly assign half of the responders, these rare cases, in the training sample. So if there were 100 of them, 50 of them are put into the training sample. And then among the non-responders, an equal number, which is 50 non-responders, are also put into the training sample. So we have 50 responders and 50 non-responders. Now, the remaining responders, the remaining 50 of them, will go into the validation sample. And the non-responders also are going to the validation set, all of them, so that in the validation set, actually, you don't have an equal distribution of responders and non-responders. Right, so this is the actual mechanics of creating the training set and the random set and the validation set. Now, evaluating model performance when using a non-oversampled validation set, which is typically suitable for model performance when the number of responders are exaggerated. So we want to make sure that we are evaluating model performance using a non-oversampled, and then we are also evaluating model performance if only oversampled validation set exists. So both kinds of validation sets, we would want to evaluate performance. And we train the model on oversampled, but validate in the regular data in this case. Whereas in this case, we train the model in oversampled, and then validation set also, we could look at the oversampled, and then we can compare the model performance in both of these cases. So there are, I mean, different techniques. We have yet to get to all these models, but I'm just trying to provide you the essence of it, the idea of oversampling. At this point in time, we have not done any of the models, so it might be a little bit more difficult to assess or capture all the intricacies. But as we get further, we will know more about this. So the way we adjust, as an example, I was talking about the weighting earlier. This is how we will adjust for the oversampling typically. How do you weigh and then reweight it so that the oversampling can be removed, or something which is resulting from oversampling can be removed, and we get to understand the model in its originality. Suppose we have responders who are 2% of the whole data, but sample we are using 50% of them, right? I just mentioned that when we are doing the training set, we want to make sure that we take this rare class, but make them 50% of the training set. So that's 50% of the training set. Non-responders are 98% of the whole data, but 50% of the sample. So this is what we have ensured our training set will be. How do we create weights? Now, each responder in the whole data is worth 25 responders in the sample, right? Because we have this 50% in the sample and 2% in the whole data. So 50 divided by 2, each responder that we have in the whole data is worth 25 responders in the sample. So that's the ratio, 50 divided by 2. That's this ratio. Whereas each non-responder in the whole data is worth 50 divided by 98, which is 0.5108 non-responders in the sample. So that's the ratio that we are taking about how much did we use in the training set and what's the actual percentage in the whole data. So that's the two weights now we have, 25 and 0.5102. So these are the weights that we can use to adjust the confusion matrix for oversampling. When we specifically oversample because we want to capture the rare class, we want to adjust it later. And the way we adjust it is as follows. Suppose we have the confusion matrix of oversampled data for the validation set, which results in a value like this. We predict 0 when actual 0, 390 of them. We predict 0 when it's actual 1, 80 of them. We predict 1 when it's actually 0, 110, and predict 1 when it's actually 1, 420. So the errors are these two, 110 and 80, right? So 110 plus 80, 190 divided by total of 1000. We have a 19% misclassification rate. And the model ends up classifying 53% of the records as 1% as ones. Now, adjustment is done as follows. We have found the weights here, 25 and 0.5102. So for the class 0, we weigh these values 390 and 110 by dividing it by 0.5102, both of them. So we get new values here, 764.4 and 215.6. For class 1, which is our responder, where the weight was 25, we are weighing it by dividing each of these values by 25. It's 3.2 and 16.8. So those are the values here. Now the adjusted misclassification rate will be 3.2 plus 215.6 divided by 1000, 21.9%. And the model ends up classifying 23.24% of the records as ones when we assume 2% responders. So although this shows as a very high classification here, after adjustment, we can see that this is the real performance of the model. So we want to make sure that we reweight it and then capture the performance of the model. So that's something which we do as part of the model creation. We adjust the lift curve also for oversampling. So we just adjusted the confusion matrix in the previous slide, but lift curve that we have created can also be adjusted for oversampling. Sometimes it's very useful measure in low response situations, specifically when we are interested in not so much in classifying all the records correctly, but finding a model that guides us for records that most likely contain the response of interest. So whatever the important classes, can we get a model which captures that part? So because sometimes the resources are very scarce to capture or go to every single responder or send mails to every single one. So lift curve sometimes is a better metric because it gives us the lift that we get by using a data mining model. So we can adjust these lift curves also for oversampling when we oversample, and there's a procedure. We sort the validation records in terms of the predicted probability of our success, because that's the whole goal of lift curve, that we always put them in a descending order of probability of belonging to a class. Then we record the cost associated with the actual outcome for each record, that list that we have just created. And now what we are doing is divide the value by the oversampling rate. So we just found the weights were 25 and 0.51. So in this case, responders are overweighted by a factor of 25. So we divide by 25. So that's something which we just talked about, the lift curve with cost, but this one is lift curve with cost and with some reweighting. So reweighting is with the help of that weight that we just calculated. So that's something which we can do. And then we keep going from the highest probability first record to the next record, and then keep doing that step, which we just talked about, and then look at it with reference to the diagonal line, how much benefit we are able to gain after having reweighted it for oversampling. So that's sort of overall discussion that I wanted to have about um, different performance measures, how we look at it, how we go about trying to adopt some of them depending on the objective of the model, whether it's prediction, classification, ranking, and how do we consider oversampling in certain cases? What do we do after oversampling for adjustments? So whole slew of things we covered, and there is reading for this that you have for deeper understanding of it. There are also codes that are provided to you so that you can exercise them and try to find some of these uh, performance measures for simple data sets. In fact, in your assignment, you will be working on something on these lines.